Joe is one of the organizers, I said the main organizer of this activity, and since he's not going to talk next week, so we asked him to give a presentation this week, and he's going to talk about the Transplanckian Excursions on the visitor space.
Okay, so thanks for the introduction. Okay, so this is going to be a talk about two papers by myself, so one from October last year and one from March of this year, and the talk's going to be roughly divided in half according to these papers. Okay, so first part, why should we care? Well, all this talk is motivated by one observable, conventionally denoted R, which is the tensor to scalar ratio. So in the study of inflation and the observation of the fluctuations in the microwave background, you've got a ratio of tensor perturbations which have not been observed to scalar perturbations which have. And the reason this quantity is interesting, if you like to think about string theory, is that this observable is related to the displacement of the inflaton in field space during inflation. So as you have a conventional inflationary picture, as you roll along, and then you come down, and then you reheat. And during inflation, the inflaton moves a certain distance in field space, and the distance it moves in field space then determines, or can be related to, the tensor to scalar ratio. And why this is interesting in string theory is that you have a factor of m Planck here, and I regard it as generally good motivation to think about something in string theory when you see explicit factors of m Planck appearing. Now, there's another reason for thinking about this in string theory, which is the question of, is it possible to build such large field models where the inflaton displacement is parametrically bigger than m Planck? So is delta phi very much bigger than m Planck possible?
Hey Joe, what's the current limit on R?
Is it about 0.1, something like that? Is that kind of order? I don't know. Planck's going to take it down to roughly this sort of 0.01 level. Whether they do it immediately or over a couple of years, I don't know. But I think currently it's around 0.1. But I'm not.
Limit is 0.13.
0.13. Right. Okay, so then we have this question. Well, can you actually get these substantially Transplanckian displacements? So one reason for kind of thinking this might not be possible is that if you look at kind of lots of string models of kind of motions of moduli, you realise that moving through a Planckian distance corresponds to something kind of funny happening. So, for example, various models, inflation models, so say things like branes moving through a Calabi-Yau, you realise that a Transplanckian distance is on some level roughly corresponding to moving the entire distance of, so a Planckian distance is roughly moving through the entire distance of the Calabi-Yau. Again, with moduli, if you have some, say, small cycle and you want to blow it up, well, getting to a Planckian distance corresponds to making the cycle almost as big as the whole space, so you can see that something screwy is happening. And then also other models like branes and warp throats, again, you can never kind of get this, you can never get this parametrically large. One thing I should comment is that one way where you do have unbounded distances in field space in string theory is in decompactification or weak coupling limits. So, as you can run away. And here you'll find that if you want to say something like the volume modulus or the dilaton, if you want to move those through a distance m Planck in field space, that corresponds to, on some level, kind of reducing the string scale roughly by a factor of E, or reducing the string coupling by a factor of E. So essentially what you're doing, you're seeing that this is, if you want, okay, you do have a Transplanckian distance, but it's very, very hard to keep it flat, because moving the Transplanckian distance, is making a complete change in the theory. Okay, so all this motivates thinking about whether it is actually possible to have large field inflation in string theory. Of course, it's possible to do it in field theory. You just write it down. I mean, that's how field theory works. You can just write things down and then say, well, this is how it is. But string theory is harder.
But even in field theory, there is a question of naturalness.
In field theory, there's the question of naturalness, but if you're Andre Linde, you can just say, well, m squared, I have m squared, phi squared potential, and this is valid for arbitrary large values of phi, and this is my model. Yeah.
So when you take phi much bigger than the Planck scale, it's presumably much bigger than the string scale as well, right? And so you're probably not going to use a supergravity description anymore. You have to use a string description.
Yes. Okay. Yes.
So the energies are smaller.
Yeah. I mean.
Yeah. That's when a no scale model you can have it.
Well, I mean, the standard Coleman-Weinberg description is if you want to describe phi to be very large, right? You look at the renormalization group at the renormalization point, which is of order phi, right? And now phi is much bigger than Planck scale, so you affect the theory that scale must be the string.
So in terms of effective field theory, you can't make phi much bigger than m Planck because you have basically operators like this, which are Planck suppressed, and once phi becomes bigger than m Planck,
That's in a field theory.
That's in a field theory. Yeah.
And then once you get to scales that big, you're going to have to discuss the string.
Yes. So if you want to actually have a theory you can trust, you have to be doing it in string theory. Yeah. Okay, so this is what motivates. This is a kind of a question of thinking. Well, is this likely to be possible in string? So so then the first part of my talk, I want to discuss. Okay, so there's one proposed model of doing this called axion monodromy inflation, and so my paper of October argues that this model doesn't really work. And so the first part of this talk, I want to kind of basically explain the argument against that particular model. And then in my second part of my talk, I want to talk about my more recent paper, which is kind of trying to give ways of thinking of kind of from a more general kind of quantum gravity perspective, what kind of problem you could have intrinsically with Transplanckian flat directions. Okay, so first of all, I want to talk about the issue of brane back reaction in axion monodromy inflation. Okay, so here I'm going to just kind of pick out the details of this model that are relevant for me, and then explain what I think the problem is. Okay, so
This scenario is for just after the Big Bang, right?
yes, yeah. So this is in inflationary.
Yeah, the usual.
Okay, so first of all, what's the idea of this model? So the rough idea is that if you want to move through very large distances in field space, you need to be protected in some way. You need to protect yourself against corrections to the effective potential of this form, because if such corrections are present, they will obviously kill you. Or they will kill a model of trying to be flat across Transplanckian field distances. So one of the good ways of protecting flat directions are symmetries, specifically shift symmetries, due to axions. So the idea of this model is to basically use the axionic shift symmetry, but then have it broken by something, but so that the symmetry is sort of still there at some level and can protect the flatness of the potential across a very large distance. So use axion shift symmetry, and then it's broken by a brane, in this case the NS5 brane, and the inflaton can be an RR or an NSNS2 form.
The field manifold for that action is not compact or compact?
So the compactification manifold, the overall manifold is compact, but
Field manifold.
The field manifold is non-compact.
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 Only the action has the compact field manifold, the periodic.
Yes. Yes. So what the idea is sort of that you have you have the kind of you have a 5 brane which basically explicitly breaks the axion shift symmetry, but it's still there. But in some sense, this is the only thing that's breaking it. So you then have some kind of linear potential coming from this bit which breaks it, but other corrections are protected from the sort of legacy shift symmetry.
So it's totally different from its breaking, for instance, by instant.
Yes, yes. Which still leaves the periodic 2 pi shift symmetry. Yeah. Yes. Yeah. And then so what drives inflation is the dBi-ish action for the NS5 brane. So you have a 2-form basically present on the 5 brane. So you have a 2-form, an axion field on this 5 brane. As you turn up its VEV, this basically enters this dBi-like term to increase the tension of the 5 brane. And then as you make this larger and larger and larger, this becomes linear in C at large C. And then the idea is that such a linear potential will then drive inflation. Okay, and to suppress the energy scale, because if the energy scale is at the string scale or the Planck scale, then that is obviously problematic for describing something in a supergravity framework, then the 5 brane is down a warp throat. So, and there's another final piece of this construction, which is the part I'm going to focus on, so I want to emphasize this, is that you place the 5 brane that source on a 2 cycle, that source is a tadpole. So you have a 5 brane on a 2 cycle, which sources a tadpole. To cancel the tadpole, you have a distant 5 brane on a homologous 2 cycle.
Sorry, Joe.
Yep.
Why is it linear in C at large C? If I take det G plus C.
Well, it's C squared. It's C squared under the square root.
Is that?
Right.
Is that?
But even then, if I take the determinant of that, then I get things, because remember, it's square root det G plus C, right? And then.
So okay, so this is slightly.
Much higher order than C.
So hang on. So C is only present in the compact dimensions. So let's see. So when we expand this, we're going to get the 4-dimensional. The 4-dimensional part of this is going to get pulled out, and then the rest of that.
Yes, I think it's the terminal G plus B in 2 dimensions. Then you get.
So you're saying C is only in the 2-dimensional part?
Yes.
Okay.
Yeah.
Then that's right. Because then you get det of C, a 2-dimensional thing, which is C squared, and take the square root, which is C.
Yeah.
That's right.
Yeah.
Well, depending on how you sell it, you can be the square of the.
Yeah.
Once you did that square, when you did the terminal.
C is only in the 2-dimensional thing.
Okay. Yeah. Yeah. Okay. So then this model basically an intrinsic part of this model, which is the part I'm going to criticise, is the idea that you put the 5 branes down, the NS5 branes carrying the axiom to drive inflation down a warp throat, and you need with an anti-brane down a homologous warp throat. So you have this 2 cycle which is sort of down what is kind of banana shape, where it's down 1 warp throat and then it stretches out, goes into the bulk, and then comes back and goes over here. So the tadpole is sourced here and cancelled here. So this is important. So this is in distinction to something which occurs, say, like anti-3 branes in Klebanov-Strasler, for example, where if you put an anti-brane down the throat and the throat itself carries lots of charge. So just a sort of contrast. So KS with a anti-3 brane. So remember that in something like KS, there's lots of 3 brane charge filling the throat, and so there's a source. The anti-D3 brane gives you an anti-D3 tadpole, which is all cancelled locally in the throat. Okay, so then this is then a question on then brane back reaction and effective brane anti-brane potential. So the argument I'm going to make is that if you put such branes, even if you put them down the very bottom of a very long and deep throat, that their potential, the interaction energy of their potential is actually at the string scale, the bulk string scale, not the warp down scale. So that even though these branes are at the bottom of the throat, the interaction energy between them has got nothing whatsoever to do with the warp scale. The warping is in some ways simply a confusion, that their interaction energy is all set by the scales up here, not the scale down here. So if this is the warp scale, and this is the bulk scale, then the claim is that the mutual interaction energies of these are all set by the bulk scale and not the warp scale.
So, why is that? Why is it that the bulk scale is irrelevant?
So it's going to be related to the fact that the tadpole is sourced down one throat, the tadpole comes out into the bulk.
Has it something to do with the fact that you've broken supersymmetry also?
It's not particularly to do with the fact you've broken supersymmetry.
I mean, wouldn't that tend to decompactify the space? Would it be a potential which will tend to decompactify?
Okay, so these sorts of questions are, I'm going to sort of basically to make this argument, but I'd like to kind of ask, are there other questions before I give the argument that the warp scale has nothing to do with the...
We're concerned whether that's wine, Joe.
You're concerned why it's wine, or
whether it's wine, or
Why is it red wine?
why is it red wine? Well, it's red wine because, on the one hand, seminars, are meant to have this lively, interactive spirit, which wine encourages. And secondly, as I'm sure you know, there's a good tradition of drinking alcohol when giving important talks. So, yeah, this has nothing to do with physics whatsoever, but you may know it's a tradition in Britain that basically every year when the Chancellor of the Exchequer gives the budget speech announcing what the budget will be for the next year for the government, he has an alcoholic drink while he...
That explains it all. See the economics.
Okay, but anyway, any other questions? Okay, so right now let me give the argument that this is going to be at the box scale. Okay, so we're thinking about interaction potentials between brane and anti-branes. So I'm going to give a couple of arguments to this. Okay, so first of all, just first of all, if you think about something like something like a D3 or an anti-D3. So one way you can think of it is that there's a charge associated to the D3, something which propagates out, and then eventually you see the back reaction of the D3, in that it sort of sources perturbations in the metric, perturbations in the form fields, perturbations in the stress tensor. It's going to carry on doing this until it sees the object which cancels its charge. So when you kind of think, so then in open string language, if you compute, say, the interaction between, say, a D brane and an anti-D brane, the diagram that does this is the annulus. Yeah. You have one loop potential energies, and string theory these are computed by one loop diagrams, and if you have a brane and an anti-brane, the only one loop diagram that can be is the annulus. So you can look at this as you've got kind of open strings which stretch between the brane and the anti-brane, and then you've all possible loops of these, and this then gives you the interaction potential energy. From a closed string point of view, you source closed strings, these propagate across the space, and then see the anti-brane. Okay, so now let's think about this picture. Okay, so the key point here is that there's a tadpole sourced by the 5 brane on this cycle. So this is a non-supersymmetric brane, but it's also sourcing a tadpole. And tadpoles are topological objects. In a sense, there's charge quantization. So there's an integer charge associated to this tadpole. So if you think about what happens as you move up the throat, then the tadpole also moves up the throat. And because tadpoles are topological, so this theory could be completely and totally inconsistent at this point, because if you didn't cancel the tadpole, then the theory would be dead. So you can carry on going up the throat, up the throat, up the throat, up the throat. And so let's draw kind of like, if you like, a circle around the top of the throat. Now you're in the bulk unwarped scale, and say, well, can we see the effects of the anti-5 brane on this circle? And would these effects be suppressed? So if you like, this is a bit like, I mean, if you're thinking about sort of like gravitational physics or black hole physics, this is a bit like having a big ADM sphere at infinity surrounding, in this case, the warped throat. And you say, well, what are the effects of this object here? Now the point is, because it's wrapping a cycle, and because this cycle is topological, the charge is unwarped. The charge on the 5 brane is unwarped. So when you get out into this bulk region, you will still have this unwarped charge still visible. So what you will get is then you will get a non-SUSIC perturbation to the bulk metric, and this perturbation also has to be unwarped. And the reason it has to be unwarped is because you're saying, well, you're measuring charge at infinity, and you can't warp down charge. So as an analogy, if you have a black hole and you have an electron spinning around, if you have a neutral black hole and you have an electron spinning around with some accretion disk just right next to the black hole, and you say, well, what's the form of the metric and the stress tensor and so on sourced by the electron far, far away from the black hole? So even though near the black hole you're in a highly redshifted, a highly warped regime, so this is a warped regime, so this then has to be an unwarped perturbation, because the charge on the electron is topological, and so the charge on the electron is not at all warped down as you go far away from the black hole.
Is this just Gauss's law?
Yeah. It is just Gauss's law, yeah. I mean, the fact you're deep in a warped regime, you come out of the warped regime and Gauss's law still holds, and you still see the charge as a completely unwarped perturbation.
So Joe,
Yeah.
so you're just saying that the NS5 brane charge is conserved in this background as opposed to the D3 brane charge, which is not conserved.
So I'm saying that as you come out the throat, yeah, that the NS5 brane charge is conserved, yeah.
Okay, so if it was a D5 brane charge, because of some orientifold somewhere, we would expect to have a anti-D5 somewhere. Is that the other one, or is it happening anything like this here or not?
So
the orientifold free plane would map you a D5 brane
Yeah.
and anti-D5 brane. So
Yeah.
And is it what you are drawing here? That's not anything to do. Is there another NS5 brane or NS5 brane?
So in the model that's put forward, basically you have an NS5 brane down one throat and an anti-NS5 brane down another throat, such that the tadpole is cancelled here.
Okay.
Yeah.
So, but they are not related by any orientifold.
Not necessarily. I mean, this argument doesn't really depend on whether these are related by an orientifold symmetry or not. I mean, what this argument depends on is that you have a homologous cycle that starts deep within one throat, comes out into the bulk, and then drops deep within another throat. And then the claim is that because the tadpole has to escape and it can't be cancelled in the throat, when looking at the kind of effective interaction potential or mutual back reaction of the brane and the anti-brane, the charge is unwarped here and the charge is unwarped here. So what you're then dealing with essentially the same problem of these are then mutually non-SUSY perturbations to the supergravity fields at the bulk level, and so that the energy scale for this interaction is then set by the bulk scale, the string scale, rather than the warp down scale.
I don't see the difference between the NS5 and the D3s.
So with the D3 with Klebanov-Strasler, so you put an anti-D3 at the bottom of the throat, but you're putting it in a Klebanov-Strasler throat. And a Klebanov-Strasler throat is sourced by ND3s and M basically fractional d5s. So then you add one d3 bar to it. So basically you've got this enormous distribution of d3 brane charge throughout the throat. So the tadpole cancellation is local. The charge on the anti-D3 brane is cancelled deep within the bottom of the throat.
And whereas these throats don't have anything to do with NS5.
But yeah, by construction, in this throat, the tadpole is not cancelled within the throat. The tadpole escapes the throat.
So sorry to insist, but in this kind of competifications, orient default map NS5 brane to anti-NS5 branes or not?
I think not necessarily. No, I mean I think these are both basically non-supersymmetric branes.
Okay, but supersymmetry is not an issue here. I'm telling that you need an image of most branes in orient default. So is it?
I'm going to pass on. Yeah, that I'm going to pass on. Yeah.
Okay, so if these two guys, imagine that I identify these two throats by an orient default action.
Yeah.
That's not what these people in the axial monodromy want.
No. So there's another way to phrase this argument. So that's a more kind of closed string way of phrasing it. So there's a more open string way of phrasing it. So okay, so in the model it's kind of NS5s and anti-NS5s, but I'm going to say that the morally this should be the same as kind of D5s and anti-D5s. And for D5s and anti-D5s, okay, so you then can use our string intuition. And this picture here, I said that in string theory, the interaction potential between branes and anti-branes you can compute via the annulus one-loop open string diagram. So what is this diagram? Well, schematically it's very simple. It's an integral over the modular parameter of the annulus t, and then you basically integrate over all the modes that are stretching between the brane and the anti-brane. So you've got this integral here, and then you've got a mass scale coming from the modes that are stretching between brane and anti-brane. Okay, now the point is that, yeah, and this is just how you compute interaction potentials directly in string theory on the world sheet. Okay, so if you say, well, I now want to draw an open string stretching from a brane here to an anti-brane here, well, what's it going to do? There's only one thing it can do, because these are sitting in different throats, is it has to come out of the throat, head into the bulk, and then head back into the other throat. And in particular, it spends some time in the bulk regime. And in the bulk regime, it's got some bulk length. There's no warp string scale in the bulk. So the mass of this string is set by its classical tension. And it's because it spends some time in the bulk, the mass of this string is, now there's some length, if I call this length here, L, is basically L times the string scale. And this is the unwarped string scale. So what this then says is that all the strings that contribute to this diagram have unwarped masses. And so because they all have unwarped masses, this mass is an unwarped scale.
For 1 minute, Joe. I mean, can't you just do that calculation and actually calculate the effective length, and that will include some contribution from the non-bulk bit?
It will include some contribution from the non-bulk bit, but because this, okay, so you can't, but this, because this is all warped down.
Yeah.
So this would give kind of very, all I care about is that there will be at least this contribution from the bulk bit.
That's for sure.
Yeah.
Oh. Okay.
So that's all I care about. Because if I say that there's at least this contribution from the bulk bit, then the mass is at least that big. So because this has got e to the minus m squared t, this integral only gets contributions from t being approximately 1 over m squared, where this is a bulk string scale. And so viewing this as a one loop integral, the only region of parameter space which actually contributes is the energies corresponding to the bulk scale. So the only scale in the problem is the bulk scale. And so the only thing this can evaluate to is something proportional to the bulk string scale. Because this is basically forcing us to be the only scale in the problem.
But you've agreed that you do have lengths and a contribution from the bit that's not in the bulk. So you may say, So there is a contribution there, which is a bit with another scale.
Yeah. So basically, so any string that's contribution, any brane anti-brane string, has a mass which is length on some unwarped length.
Plus some other bit.
Yeah. Plus L prime
Yes.
warped.
Exactly,
Yeah. Yeah. But now, so the point about it being a warped down thing is that the string scale in the warped region is very much lower than the string scale in the unwarped region. So this is then, okay, this bit is then very much smaller than L over square root of L.
That's the bit I need,
Yeah.
yeah. Okay,
Yeah.
good. Thank you.
But what happens, so you have a potential, you're saying, which goes like L, capital L, right?
So I'm saying that the only strings that, in this diagram, all the contributions are set by this scale capital L. Yeah. So this is the only scale in the problem. And so because this is the only scale in the problem, the interaction potential must be set by the only scale in the problem.
But can I understand the picture is really describing what happens? What if L goes to 0? There's no, the two throats just come together?
So as the two throats come together, then, okay, so then you'd have some kind of picture like this. So then you'd always be set by the highest scale in the problem.
By the high scale?
By whichever is the highest scale, basically, whichever is the least warped regime of the geometry.
I mean, you're going to try to say that this thing eventually, these two things, throats annihilate, or
No. So all I'm going to say is that is basically this model, which is kind of built on this geometry, and on the assumption that basically, when you turn an axion on here, the contributions to the potential you get are all at the warp down scale. This model isn't correct, and that this doesn't work.
okay.
And when this doesn't work, then this particular attempt to realise large field inflation in string theory doesn't work. Which is another bit of evidence that string theory doesn't allow large field inflation.
You don't have any chance that you have some supersymmetric Lie stored in the bulk? No chance for that?
So these are, I don't see that that's kind of relevant because these objects are just mutually unsupersymmetric. I mean, they're just, they basically break supersymmetry as badly as you can.
The reason they wanted a throat was because they wanted a work factor in front of the potential.
Yes.
Of
Yeah.
flatten out potential.
Yeah.
So what you're saying is that that's irrelevant. So you should, it is the same as not having throats, and then it's a potential like that, but it's very steep.
It's a potential like that, but it's at the string scale. And then, so then you have, okay, yeah, then it's the thing of do you believe, and if you basically put branes and anti-branes in the bulk, so all your potential is at the string scale, is that consistent with a supergravity treatment of moduli stabilization, etc., etc.? And I think, yeah.
Going back to my question before about the Kavanaugh-Strasser, in that case you say that you have Kavanaugh-Strasser, you have D3s and D5.
Yeah.
So you would have done this with D5s, you could have cancelled the totals locally.
Yeah.
But that doesn't work for inflation.
So another reason why they need to go into the bulk is because the axion decay constant is set by this bulk scale. Because you can also think that if you do everything locally, also the axion decay constant is also warped down. So then to actually reach a Planckian distance, if you've warped down the axion decay constant, to reach a Planckian distance, you then need to move an enormous number of monodromy steps.
Right. So it's like you have, on top of this potential, you have the cosine potential of the action. The scale of the cosine potential of the action will come also warp, and then the two warp things cancel.
Yeah, I mean, so the way this kind of would work is because in sense this tries to work is that the decay constant is at the bulk scale. So the number of times you need to do the monodromy step is some level set by the bulk, the relation between the bulk string scale and the Planck scale. But the potential they want to have at the warp down scale. So then every time you do a step, it doesn't really affect anything very much because everything's warped down. But so what I would say is that either everything's at the bulk or everything's at the warp down scale. But you can't get this kind of fortuitous combination of the decay constant being in the bulk and the potential being warped down. Okay, so I now want to move from the particular to the general and talk about this other paper. Okay, so so far I was dealing with kind of arguments against a very specific model attempting to realise large field inflation in string theory. So now I want to try to think about what more general constraints can exist on inflationary models coming from quantum gravity. Okay, so the argument is going to be entropic in nature. Okay, so first of all, let me give us a slightly the sort of, well, the intuitive way of, you know, what kind of leads me into this problem. Okay, so de Sitter space has an entropy. So any realisation of, okay, this is holding for eternal de Sitter, but inflation is at least well approximated by eternal de Sitter.
Entropic, not anthropic.
What is
Entropic. Yeah. So de Sitter space has an entropy. Which, for a given Hubble scale, is set as so. And so this is the analogous of the black hole entropy. And so this is giving you some level. There's some quantum gravitational measure of the number of degrees of freedom that are associated to any realization of de Sitter space.
Joe, very stupid question perhaps. Is it the de Sitter space of inflation, or is it the de Sitter space of 10 to the minus 120 and 9 to the 40?
So this is any model of eternal de Sitter.
But does it matter anywhere whether we live now in...
No, so it doesn't matter what the Hubble scale is. It doesn't matter.
But also the sign of the cosmological constant.
The sign?
The sign as observed.
It's de Sitter space.
Yes, it is now, but suppose we lived in not de Sitter space, would there be any change in your argument?
So this entropy wouldn't exist, so...
Yes,
yeah.
So then what?
So the argument I'm going to give, which is based on this entropy, would not apply.
It would not apply if lambda was just a tiny bit smaller than, instead of positive 10 to the 120, minus 120, would be minus 10 to the 120.
So I think what I'm going to say about inflation would be unaffected. Because inflation, in that inflation is well modelled by eternal de Sitter space, which is I think which is at least a reasonable approximation. But
I'm still puzzled that such a tiny difference can destroy the argument. But
I'm confused now. So you are talking about inflation.
Yeah.
Yes.
So you're talking about the vacuum energy, which is
that's what I'm asking you.
Yeah.
It has nothing to do with the vacuum energy of our world. This is just de Sitter.
Yes, but this de Sitter entropy, the given Hawking entropy applies independent of what h is.
Yeah, but would it make any difference then? So suppose they had observed that lambda was negative, then you would not be making this argument now.
No, so what I'm going to say is about inflation.
Yeah.
Yeah.
I know. But
yeah. Let me kind of carry on. And then we'll sort of see whether. Okay, so this is kind of a sense. In some sense, there's a maximum number of degrees of freedom that you can have in de Sitter space.
Sorry, but degrees of freedom of what? Of the scalar field or the inflaton or what? What has degrees of freedom?
Well, in some level, everything. In the same way that the black hole entropy is a measure of all the possible ways of making that black hole can be.
Yeah, but in the black hole there is something. There is mass.
Okay. So I'm going to give what I'm going to use as a kind of an operational meaning of this in a moment. But first of all, I want to kind of basically put a couple of questions to try and make this more sharply posed. Okay, so if you have an inflation, so suppose you have an inflationary model. So suppose you're a field theorist, and you build an inflationary model, and as a field theorist, you can put any number of fields there, if you like. So you say that you have n fields, and these are, say, with and these fields, you've got n fields with either a kind of a periodicity or some kind of cutoff scale, lambda. And so a question you can ask is, how does the entropy depend on, how does the contribution of these fields to the de Sitter entropy depend on the number of fields and the periodicity or the cutoff? So on some level, I think it's intuitively clear that if you've got a model with kind of 5 fields, then that's got more entropy, or that's got more microstates than a model with 1 field. And likewise, that if you've got a model with a kind of a field range of, say, a field's got a field range of 100 MeV, and you've got another one which has got a model with a field range of 10 to the 16 GeV, then the model, the field with field range 10 to the 16 GeV has got at some level more microstates than a model with a field range of 100 MeV. But so now the aim is to try and make this a little more precise. Okay, so...
Sorry, Joe,
yeah,
I don't quite understand that, because normally when I talk about microstates in a microeconomical ensemble, then I'm looking at number of degrees of freedom per delta E in energy. So when you're saying I've got more things because I've got more energy range, you're in some... What's going on? You're saying, if I'm in a microeconomical ensemble, then I look at the number of states per delta E. So it shouldn't matter whether I allow my fields to have.
Yeah, but the entropy is log of the number of microstates, and the number of microstates.
So first of all, right. So the de Sitter entropy is meant to be finite. Yeah. Okay. So can I first of all give an argument to say that if you had infinite field range, this might be a problem? Okay, because so if you had infinite field range, so you can construct you've got an exactly flat potential. So I can put the field, say, on some VEV, and I say, well, on some level you can say that you can construct states by basically what the VEV of the field is. So then I can start enumerating realizations of de Sitter space, which are basically given by having the field having every possible VEV. So, so on some level, this is completely crude, if you like, but phi equals 0, phi equals 1, phi equals 2, phi equals 3. And, in that you believe that a quantum field with a VEV of 0 is a different state from a quantum field with a VEV of 1, is a different state from a quantum field with a VEV of 2. Then I would just enumerate this way, with an unbounded field range, I would enumerate an infinite number of states, all of which seem to be consistent with the realization of de Sitter.
These are the classical values of the field?
These would be classical values.
And what about one-loop contributions to the...
So if I just take an arbitrary field theory model where I have a totally flat potential with no interactions.
They still get one-loop corrections to the vacuum energy.
But how's it going to break the... if I have a field with just an exact shift symmetry, that's going to just remain flat always.
What is this that's remaining flat? This is the potential?
Yes. So if I just said ad hoc that I have a field theory which has got one field phi, and it has a potential v of phi equals v naught greater than 0, and I'm going to be even more ad hoc and say that this is its exact quantum potential.
Oh, okay.
Yeah. But then if I could do this, then I would say that on some level, if it's got an infinite field range, I can associate an infinite number of possible states to it. And infinity is bigger than a finite number.
For 1 minute. I mean, normally what I do is I write down a partition function. And then when I write down a partition function, normally I do not integrate over 0 modes. And I sort of remove their volume. So what you're telling me is that you're including those in the partition function, which you're normally told not to do, because that always gives you infinity.
So normally in field theory, super selection sectors you discard. There's always, like in field, there's a super selection sector which is the VEV at infinity, and that bit you normally take away when counting states. So what I will say is, I think that in de Sitter space, I think this is the wrong thing to do. And also remember, that one thing I just want to kind of emphasize and re-emphasize this point is that the de Sitter entropy is totally different from a thermal entropy in some way, because there's a de Sitter temperature as well, and with the de Sitter entropy, as the temperature goes to 0, the entropy goes to infinity. So in the limit of the de Sitter entropy, as you make H larger and larger and larger, the de Sitter entropy goes. So the de Sitter temperature is H. So as you take h to 0, which is as you begin to approach the flat space limit, the de Sitter entropy goes to infinity, which is giving you an infinite number of microstates. And this is totally different to the normal behavior of a thermal partition function, which, as you take to 0 temperature, does not give you an infinite entropy. But so what I would say is the way I would interpret this limit is that these are, because, okay, let me just, a bit more thing just about in relation to this is that, okay, so this is a gravitational entropy. So de Sitter has a horizon, so you have a de Sitter horizon. And on some heuristic level, we know that in gravitational entropies, the entropy you should associate to degrees of freedom on the horizon. So as you take the t goes to 0 limit, the h goes to the 0 limit, and the horizon moves out to be infinity. So you should want to associate then the entropy on some level to the degrees of freedom at infinity as you take the temperature to 0 and you recover flat space. And I would say that these are precisely the superselection sectors. So that as you take the temperature actually to 0 and you recover flat space, you'd be saying the de Sitter entropy should be associated with modes of the field at infinity. And those in flat space are precisely the superselection sectors of quantum field theory.
The black hole entropy, that's supposed to be coming from de-brane configurations and strings between them and all that. There is no corresponding picture here, right? So there might be something quite unexpected, where the entropy is accounted for not by, the obvious field theory states, but by some microscopic construction.
Okay, so I think that's a line in for me to give. Okay, what I will take as my operational definition of de Sitter space, in the sense of how you count microstate, what I would mean by a microstate, and then just to argue how these things depend on this.
Does this mean you've got negative specific heat?
Pass. Probably it's a gravitational system. Gravitational systems normally have negatives.
No, anti-de Sitter doesn't, for example.
But black holes. I mean,
black holes do, but black holes in anti-de Sitter don't. I mean, it all comes with the stability question.
So I'm going to pass on that because I haven't thought closely enough about that. But I think de Sitter space is very much like a black hole. So suppose you have a some action or state fields. So my operational definition of de Sitter space, of de Sitter entropy, would be basically the number of ways, if you have some field theory, the number of initial states you can prepare it in, so it will asymptote to future de Sitter. So the number of initial field configurations that will asymptote to future de Sitter space, to future eternal. So remember that de Sitter always just throws everything outside the horizon.
If you apply that definition to black holes, will it give you the right answer?
Black holes are kind of, again, can I pass on that, because I mean black holes are kind of, de Sitter throws everything. Black holes take everything inside the horizon, and de Sitter throws everything outside the horizon.
Can you just say there where your initial field is defined? Where's the Cauchy surface?
So
it's probably related what you just said.
Okay, so again, I'm going to want this to be kind of a quantum mechanical statement. Maybe it's if I just kind of carry on with what I'm.
Right.
So, in a sense, I don't have a kind of sophisticated GR way of.
No, I'm just trying to. When you say initial field configurations, that's got to be defined somewhere.
Yes. Okay. So the sort of thing is in something like R space. So what happens as you go forward in time, with is that this is us here, and these are the galaxies, and over time the universe will just throw all the galaxies outside the horizon, and we'll be left with just us sitting in the universe with its current cosmological constant. So what this means is that to say that the number of kind of you know, this is one state, this is another state. But all these are kind of possible, you know, states of the field theory now, but they will all end up in the same eventual configuration, which is just de Sitter with nothing else in it. And so if I have kind of, you know, the standard model here and now, I see, you know, so all possible configurations, excitations of the standard model that will end up in the far future as just de Sitter with nothing else in it. I'm going to count as effectively microstates, as it were, of de Sitter. Okay, so now the thing. So now here's the kind of. Okay, so remember that as the universe accelerates, things that are far off you kind of get redshifted. So things on the horizon over here, I'm only going to know about in the far future, and they'll get infinitely redshifted as they come to me. So you can, well, using just kind of basically standard quantum field theory, you can estimate about the number of kind of degrees of freedom inside the bulk, and you'll get something which is kind of very subleading. But so I'm just going to, at this point, jump to say, let's thinking about field configurations on the boundary. So for me, as an observer in this de Sitter, with my future de Sitter, you know, however many billion years away, this is things happening right now on the horizon that I will just be able to see in the future. So if I take me here, and this is my horizon, which I will see only in my asymptotically de Sitter future, and I have some field phi of x. Okay, so then the idea is that I can discretize this field, just the way you do in lattice theory. So you can take this field and you can discretize it on smaller and smaller distances until you get to basically the cutoff scale. And I can get, so then I can kind of, and on each of these, you know, unit blocks of area on the horizon, I can imagine a vector field. And I can make this field almost as kind of arbitrarily kind of jagged and spiky as I like, because by the time it gets to me, everything will have been redshifted to 0, and so won't be dangerous at all. And then I can, some level, say that the number of profiles of phi at the horizon. Okay, so if you roughly say that there are 2 possible vevs, by the time I've discretized down to the smallest possible scale, there are roughly 2 possible vevs of phi on each fundamental unit. So then I have the area of the horizon, which is 4 pi over h squared, divided by the number, the number of is 2 to the area of the horizon, divided by the length, the cutoff scale, lambda squared, to give essentially a number of kind of microstates of the field, going as 2 to the lambda squared over 4 pi lambda squared over h squared, to then give a contribution to the entropy from phi, which goes as log 2 times 4 pi lambda squared over h squared. Okay, so then this is an argument to say that if you have a field, a quantum field of with a cutoff scale lambda, which in models like axions, for example, is often the same as the field range, then this will give you a contribution to de Sitter entropy going as the cutoff scale squared over the Hubble scale squared. There's another argument that gives this same result, which let me just give it briefly, which is entanglement entropy. So entanglement entropy is the entropy you get if you take a field theory, you basically put some big boundary and you trace over all degrees of freedom outside that boundary. So you basically throw away information about the field outside some boundary or horizon. And so here I'm just going to state the result again, that the entanglement entropy for a quantum field goes as some kind of model dependent prefactor times the area which you trace over. So if I then take the entanglement, if I take a scalar field into sitter space and I say what's the entanglement entropy you get from basically tracing over the degrees outside the de Sitter horizon, I then get an entropy for the scalar field which is going as lambda squared over h squared.
Without the log.
So the problem with the entanglement entropy computation, it basically has a prefactor that depends on how you regulate the theory. So it depends explicitly on the cutoff. And in field theory, this is just a divergence. You put the cutoff in some way. So there's some factor here that just depends on how you regulate the theory.
No, but so this one's lambda squared over h squared. The other one was log lambda squared over h squared.
Log
2 times.
Yeah, sorry. Yeah.
Got it.
Yeah. Yeah. Okay, so up to the prefactor, which is hard to defend. And so this then says, both these arguments then give the same expression, which is say that you can kind of associate an entropy to a scalar field in de Sitter space with a cutoff of lambda, and it basically goes as lambda squared over h squared. So then if you have n scalar fields, I'm getting it, so let's go to this board. So then you have n scalar fields with cutoff lambda, then this gives you an entropy basically going as n lambda squared over h squared up to some prefactor. Okay, so then the claim is that then this is then going to be problematic if this entropy, which you can kind of compute within field theory, if this entropy becomes in excess of the Gibbons-Hawking entropy, the entropy of de Sitter space. So then it's bad if n lambda squared over h squared.
Joe, would you mind using the other blackboard?
Sorry, because you can't see. Okay, so let me erase this. Okay, so. Okay, so then the claim is that it's bad if n lambda squared over h squared is bigger than m Planck squared over h squared. And then, so then this is then giving you kind of a constraint that if you try and build an inflation model as a field theorist with n fields and with cutoff scale lambda, then what you would have is that you can associate an entropy to those, which is in excess of the de Sitter entropy. There are more kind of initial states you can prepare that will asymptote into future de Sitter space than you're allowed to do, than are allowed to be by the de Sitter entropy. And so, the conclusion is that the model is inconsistent. Okay, so now let me briefly in the last 3 minutes talk about just a couple of kind of applications of this.
But Joe, you'd say the same thing about ordinary black hole entropy. If you wanted to explain ordinary black hole entropy with entanglement entropy, you'd have exactly the same problem.
Yeah.
The species problem. So you decide that you need a completely different answer, and this isn't the answer.
Sorry?
I mean, that's normally the thing, right? When people try to do this for black holes, then you realize it doesn't work because you should have arbitrary n. So then you say you need another answer for black hole entropy that doesn't come from just this entanglement entropy argument.
But in that case, people introduce a cutoff which is lower than the Planck.
So this depends on the cutoff. So,
but I can choose n to be anything. That's the problem.
well, you can choose n to, as a field theorist, you can choose n to be anything.
We choose lambda to be
I mean,
m Planck.
No, but you need to give me a
n.
reason why lambda should depend on n. Because I can choose n to be anything. In fact, because the black hole entropy argument doesn't depend on the number of species of fields that you're in.
Do you take it though as an argument that, I mean, is it an argument to say that in consistent theories of quantum gravity we know such a string theory lambda does depend on n?
But some people do claim that.
Well, it does. I mean, you just things like string compactifications, things like the Kreutzer-Klein modes, they all become light as you make the string scale low. So I mean, it's certainly in string models. I mean, n blows up as you take lambda down.
Well, I think naturally you would say that lambda is the string scale.
Exactly.
Yeah.
And when you have many fields, then the string scale should be sufficiently small compared to the Planck scale. That's the argument.
What is the inconsistency?
That is when you have, let's say, Kaluza-Klein, you have many states, and in that case you know that the string scale compared to the Planck scale will change. Low scale strings. But Twali had this argument.
Yeah,
I'm worried with things like things like that. You know that just because you go to a Kaluza-Klein scale that's small, but then you can have string states that then become light, or branes that wrap on small scales, and then you end up with more species again. So it's not clear to me. In string theory, you don't just take supergravity and compactify.
So you claim there could be many more states from string theory.
Absolutely.
Is that right?
I mean, didn't Michael and John Schwartz have a paper on this that you can't? I mean, if you just take the supergravity and then you get some scale, and then that's fine, and then you think you know what you're doing. But then if you really include the winding modes of the branes and everything else, then they're going to become light as your Kaluza-Klein things are going to go heavy, and you've got the species problem still. I mean, they weren't worried about species problem, but you're worried about whether you can control the separation of scales.
I would say that based on what we know about string theory, if you're going to argue that you can have models in string theory where you've got a very, very large number of degrees of freedom and you've got a high cutoff scale closer to the Planck scale, the onus is on you to actually produce that model. Because all the kind of easy, well-controlled examples all have the property that lambda is strongly dependent on n. Yeah. Okay, so I want to just mention some brief applications of this. Okay, so first of all inflation is an idea to get basically Transplanckian inflation by putting together a large number of axions with decay constant larger than much lower than the Planck scale to get an overall distance which is larger than the Planck scale. So basically, I'm just going to cut to the chase here, is that if you're going to get a Transplanckian distance, a parametrically Transplanckian distance in field space there, what the model requires are basically n axions of decay constant Fa, that you require n Fa squared to be very much bigger than n Planck squared. And you can see that precisely when you realise this, i.e. precisely when you start hitting the Transplanckian distances in the inflationary space, is precisely where you start getting problems here. So this is a tension or contradiction with this differentially. And another place I want to kind of flag this up is
Joe, when you say tension there, you mean that you should be able to compute the exact coefficient?
Well, yes. So there are coefficients here. So obviously whether the observable here, whether this is m Planck or 2m Planck or 3m Planck matters. Whereas these arguments are clean in the parametric limit, but not in the coefficient.
So you cannot say that this is ruled out because you cannot compute the exact coefficient.
So it doesn't say that you can't get like 2m Planck or you couldn't do this to get 2m Planck. What it's going to say is that you can't do this to get arbitrary Yeah. Okay, and another thing is then. So sometimes, in constructing kind of moduli stabilization, sometimes you have these kind of ugly gauge groups, which doesn't necessarily appear anything wrong. So, for example, things like racetrack models, for example, and I think my co-organizer might be guilty of this at one point.
Don't worry. I'm a good company.
Where you start writing down superpotentials that look something like this or something. Which involve things like, basically SU 100 times, say something like that, Or it also appears in kind of KTLT models often, where you're relying on gaugino condensation of a very large rank gauge group. So, what the potential problem here is that, if you have an SU 100 group, you have 100 squared is 10 to the 4 gauginos. So then you have, and you want this to be good in field theory. So then this is automatically kind of saying that you've got at least 10 to the 4 degrees of freedom that are much lighter than the string scale. mean, independent of other things like Kaluza-Klein replicas or anything, you mean just by writing this down, you're telling me that you've got 10,000 degrees of freedom lighter than the string scale. And so then kind of putting this into this is then telling you pretty much immediately that the string scale should be basically less than m Planck over 100. And so I think, if you look at saying some of these kind of, where the moduli are stabilized in these models, that it doesn't always seem basically to satisfy, that you put larger rank gauge groups, but then it doesn't seem that, the fact that you have a string scale which is then kind of less than the gut scale doesn't necessarily seem to be realized. So then this, I think then is a sort of tension in, this kind of stringy-inspired moduli stabilization inflationary models where you're both trying to have a high string scale, and you're trying to use things like large rank gauge groups for moduli stabilization. And of course, I should also say this also holds for like these F-theory manifolds. So sometimes people kind of appeal to manifolds with, let's say there are these Calabi-Yau fourfolds with like 10 to the 4 or 10 to the 5 cycles known, and these also automatically have the issue that you've got an enormous number of degrees of freedom, light degrees of freedom. So any model built with that needs to have a string scale that's kind of significantly lighter than the Planck scale. Okay, I'm over time. I'm going to stop. Thank you.
So, are you prepared to make a prediction that R is string theory is correct? R is.
I'm very happy to make a prediction. String theory is correct. So
that R will not be observed. That gravitational.
Okay, so there are two.
Sorry, tensor modes will not be observed.
So it's okay. So I think string theory tends against it. I mean, the caveats are that these arguments involve prefactors, and the prefactors are hard to get precise. And of course, another caveat is of course that we don't know that inflation is correct, and there may be other ways of generating. Even if inflation is correct, there may be other ways of generating tensor modes that are just not primordial. But I would say that string theory tends against getting large primordial tensors from inflation.
How will they detect this inconsistency? I mean, the inflation people, what should they have done to notice the inconsistency, other than this somewhat rough calculation? And there must be something in the model where you see things going wrong, right?
Is that just field theory, what they're doing?
Yeah.
So then they wouldn't see it.
What else would they be doing?
Then they wouldn't see it.
Why not?
Because there's a problem in string theory.
Well, I guess this
is
is
not
the kind of inflation which comes with this axionic inflation. So this is what they call natural inflation, which typically tend to have FA which is bigger than the Planck scale.
Yeah,
there is this problem. If you want to do that kind of, you want to do inflation like Klein-Seiberg or so, there is not this problem.
But what is the problem?
The problem is, as he says, that you need, in order to get a reasonable number of E-folds, your field has to be 5 times the Planck scale. It has to start in the potential. So this is what Joe would say is a Transplanckian problem. That's what he interests here the whole hour. So if you start with something which is lower, I think it's not a problem.
No, but the contradiction comes with the de Sitter entropy, right? And so when they do inflation, they're not calculating or comparing what they get to a de Sitter entropy. They don't even know how to calculate that.
I mean, there's a field theoretic formulation of inflation, which is purely kind of quantum field theoretic, and the quantum mechanics that enters it is out of quantum field theory, and so you can work with that and you can get results with that. But it seems that by construction that doesn't involve quantum gravity. I mean, the standard formalism of inflation does not involve any quantum gravitational effects. So it's not clear. I don't see any reason why you should necessarily. You should see quantum gravitational constraints working with the quantum field theoretic framework.
We had a comparison of KKLT against large volume. on your paper.
Would you mind saying?
Well, I don't see lots of it. Given everyone knows large volume is superior. Okay. No, so the thing is, so KKLT often has, so for example, is this kind of issue. So KKLT has, so say that you take the parameter just in the original KKLT paper. I mean, basically, it's an SU60. It's an SU60 gauge group that's being used for the condensation. So this means then you automatically have, 3,600 gauge nodes that are light, and so this then drives. This basically gives you then a thing that the kind of the string scale should be at least m Planck over 60. So you then get these kind of corrections which are basically going in this number 60, which because you're kind of doing this as a field theory thing, there's no actual way to calculate it. But basically, if you've got this, then there should be corrections somewhere in your action which are going as n squared, and that these are sort of invisible. Now, the difference with large volume is because the volume is much larger. So if you say something like you have a 1 over 6, a T over a 1 over 60 here in large volume, you've still got the kind of 10 to the 4 gauginos, but these 10 to the 4 gauginos, what they would tell you is that that the string scale has to be lighter than basically m Planck over 100, which is then kind of normally large volume is just always satisfied by quite a long way, because if you're dealing with an intermediate string scale or something, then you're just nowhere near that. But because KKLT is often done in the context of both that you have a high scale string scale which is close to the Planck scale, and you want to do things like gauge unification. So then it is an issue if you've got 10 to the 4 degrees and they're kind of hiding there because you just write this innocuously in the superpotential, and then you don't really do anything further. And because by nature this is a field theory bit rather than a string theory bit, so there's not a kind of a world sheet formulation for looking at the effects of this. So it's kind of a missing danger.
But there is nothing to stop them from having a much lower string scale, right?
Well, in KKLT it's hard because basically, this T determines the overall volume,
right?
And you're balancing this against W naught.
Yes.
So it's always very hard to make the volume large in KKLT because you're stabilising it by something which is exponential in volume.
Yeah.
So when the string scale is much less than the Planck scale, can you then have R which is large?
No. I mean that doesn't seem to help in.
Oh. Okay.
Yeah.
So which part of the discussion is based on string theory and cannot be addressed in the context
of this discussion? So almost none of it is, I think, based on string theory, because the de Sitter entropy is really a quantum gravity thing. It's not a string theory thing. I mean, that comes from just the old kind of quantum gravity thing, which doesn't rely necessarily on string theory.
I don't know this standard argument, but maybe I can consider another direction. So that if you have any light degree of freedoms, which covers gravity, and then you can calculate the one-loop relative correction to the Planck scale.
Yes.
Then each quadratic divergence proportion number of degree of freedoms.
Yes.
So then somehow, but in that considerations, the result seems to be kind of fine-tuning nature's problems, right? So how you get the
yeah, that's a very good comment. So just okay. So the question is in relation to so one thing you can sort of see these things in field theory is if you compute one loop corrections to the Planck scale, and you find that when you get this sort of relation, it looks like you're basically getting an order 1 correction to the Planck scale. Now, the difference between this and this is that so when you do the one loop correction to the Planck scale, you may at least hope that there's a sort of, as you say, either a fine tuning or because bosons and fermions contribute with opposite signs, so that you could cancel such corrections. Whereas with this as an entropy argument, you would expect that all fields ought to contribute positively, because any notion of entropy, the idea that the more stuff you have, the more states you have, the bigger the entropy gets, and the entropy kind of goes monotonically upwards. But both bosons and fermions should contribute with the same sign rather than the opposite sign.
If they see tensor models of Planck, what would you conclude?
So that's interesting. The one should work more on that.
The string theory is wrong.
Yeah.
No, because this is beyond string theory. So then you have to something very strange.
So I mean, also
no, but the argument.
So there are two caveats I gave, and those. Yeah. So I think it's important to try and determine prefactors in these arguments, and also kind of proposed string models of, you know, any actual proposed string model of kind of large field inflation really needs to be, you know, you really want to kind of nail down prefactors and, yeah. Because, I mean, yeah, any inflationary model gives you tensors. The question is only how large they are.
Right,
Yeah.
but I mean, it would be very difficult. I mean, it would be very surprising if you see tensor modes. If these arguments are correct, you have to have.
If you see to see primordial tensor modes, yeah. But that's another question further, whether observed tensor modes are necessarily primordial or not. Yeah.
Okay. More questions? We have a couple of hours for questions.
I have a basic question because these arguments are pretty general.
Very large.
If I look at string theory, couldn't I argue that de Sitter space in string theory doesn't make sense? As some people did at a given point, that actually string theory is either flat space or anti-de Sitter, and de Sitter, you need supersymmetry for string theory. And now the question is, on these basic questions, do you have a string theory which is consistent, which is de Sitter?
I mean, do you have? You obviously.
No.
Yeah.
It's just a question. These arguments are so general that I do not know really. You see, when the masters of the universe sometimes tell me these stories, I know that half an hour later I'm tricked. Now with you, I think you are not trying to do that.
So I don't have a theory of string theory in de Sitter space, but I don't. I mean, all the kind of work on modular stabilization. I just find. I mean, I don't see anything wrong with it, and yeah, the fact I don't have there isn't a fully explicit model. There just seems to be no reason why.
You see, this is such a general argument.
I mean, perhaps related to that, I mean, supposing de Sitter is only metastable, albeit for a long time, which we'd be happy with phenomenologically, but then in terms of then having a real horizon in de Sitter, that would be very different, because it wouldn't be in the far future de Sitter. And so it's not clear that you would really have a horizon. I mean, horizon is a global statement.
Yeah. So can I kind of make an answer to that using an analogy? Okay. So black holes we know are metastable. Black holes are definitely metastable because they radiate. But that doesn't mean that the concept of black hole entropy is a bad concept, or that black hole microstates are a bad concept. So I don't think the question of de Sitter being metastable is any kind of more problematic in terms of making arguments about horizons and entropy than black holes being metastable is a problem in terms of making arguments about black holes having entropy and microstates.
Well, it's all about the existence of the horizon. I mean,
so does a black hole horizon exist? And that's my answer to you, whether a de Sitter horizon exists.
If H-bar goes to 0, it does.
I mean, I agree. I can write down de Sitter space, and then it has a horizon. But that infers I know the asymptotic future. I mean, this is the point. It's all about the asymptotic future.
But I can write down a black hole and I know the horizon. But does that mean such a horizon exists? Is it? I mean, they seem to be the same. Yeah, one is as physical as the other.
I mean, the one is you're mixing up the fact I've got quantum corrections which give you thermal emission, which then causes the thing, and then what the classical statement is in general relativity. And the classical statement in general relativity is that you've got a horizon, and you write down the Penrose diagram, and you've got this thing, and the horizon is a statement which is about the global nature of the space and so on. And the point is that de Sitter does have a horizon, but that relies on you knowing what the asymptotic future of the space is. So it could be, I'm just saying, it could be that there is some asymptotic future where stuff happens. Fields do something, condense, whatever, stuff happens in the very, very far future, and then that wouldn't be a real horizon. And if it's not a real horizon...
But I think this is a timescale issue, because, inflation, we believe, occurred. I mean, there's kind of good evidence that it occurred. Yeah, and there was an inflationary horizon, and stuff really was thrown out of the horizon, and it really is coming back now into the horizon, and you can go up in the sky and you can measure this. And okay, so maybe in the far, far future everything's going to, but the notion of a horizon is kind of, the de Sitter horizon.
But you can't measure the de Sitter horizon in the sense of the temperature that you're looking at. The real temperature of the current de Sitter horizon is too small for you to measure. So you don't know it's there.
But inflation, inflation, the spectrum of kind of density perturbations, that's something, that is coming back across the horizon right now. You're looking at large-scale structure, you're just looking at this, and you're seeing the imprint of stuff that crossed the de Sitter horizon and is now coming back. So.
Mikkel?
Yeah, so given that we're talking about black holes, so the fact that you're finding an entropy larger than the de Sitter one, so might that mean that actually it is not just the de Sitter space, but you have the de Sitter plus some black holes that are accounting for this difference?
You mean black holes in the interior of de Sitter? I don't think so, because so black hole, the entropy goes as the area. So and remember the number of states is exponential in the entropy. So the entropy of a black hole in the interior of de Sitter goes as the area. The de Sitter entropy goes as the exponential of the horizon of de Sitter area. So as long as one's bigger than the other, as soon as you hit it with an exponential, you just forget about it.
No, but you have huge numbers of black holes in principle.
The argument was that at the end the black holes will evaporate and you can't take entropy at the end.
But I think, as long as the area, so I have some arguments in the paper about basically you try and count, terms of modes in the interior. It goes as m Planck over h, whereas the de Sitter entropy is m Planck squared over h squared. So but then once you exponentiate that gets killed.
More questions? Okay, thank you very much, Joe. You can finish your wine.